Okay, so in the last talk of this week, Aryaman Maithani will talk about Gorenstein rings.
Yes. Thank you for everyone for coming here. Thank you to the organizers for inviting me. And as the title of the talk says, I will talk about Gorenstein rings. This is something which has popped up many times in the talks over the week. And my main focus will be to give examples. I will give some sort of justification as to why these are considered when we're talking about duality. So the first section will be on something known as dualizing complexes. And the last section will be on examples. And even if you don't follow the first two sections, the examples are sort of the more fun part. And those will be very explicit and concrete, and it's genuinely quite fun to work out when something is Gorenstein or something is not in the examples that we'll see. So let's start with this. So R for me will be a commutative Noetherian ring. Most of the rings that I will consider will be Noetherian, with two exceptions that we'll see. So omega R is a dualizing complex. I'm defining what it is. If one, omega R is in the bounded derived category of R modules, which is to say that it is a complex such that it has only finitely many non-zero homologies. Moreover, those non-zero homologies are finitely generated. Omega R has finite injective dimension, which is to say that it is quasi-isomorphic to a bounded injective complex. So a complex made out of injectives, and it is bounded. And number three, the natural map from R to the derived Hom is a quasi-isomorphism. So to those of you familiar with the canonical module, this is sort of generalizing the idea of a canonical module. Indeed, if R is a Cohen-Macaulay local ring, then this will turn out to be the canonical module. The upshot of doing this is that canonical modules, the existence of canonical module is quite restrictive on your ring. This will exist for a larger class of rings. It won't always exist, but for example, take any K algebra and any localization of a K algebra, finitely generated, this will exist. So this already gives you a much larger class. And what is the upshot of this? This gives us a local duality. So as in the case of the canonical module, one considers this functor Hom. The last condition is that there is a natural map from R to the Hom omega R comma omega R. It sends an element of R to multiplication by R. And this map is a quasi-isomorphism. So as in one does with canonical module, one looks at this and this sort of supposed to be good. But as is the theme of all these talks, we're doing everything in the derived category. So we get a functor as following. I can consider a functor on all modules, but if I restrict it to the finite bounded modules, this is an equivalence. an autoequivalence of categories. This is more or less the local duality theorem. Something more can be said that this equivalence, in fact, restricts. So it takes perfect complexes to the injective perfect complexes. This is somewhat made up notation because this we know, this was defined earlier. So these were bounded complexes of projectives, finitely generated. And this is made up. Injective means just instead of projective, you use injective. But all notations are made up anyway. So we have this autoequivalence. And this is more or less the duality that I was talking about. And so as I mentioned, when does this exist? So let's look at some restrictions that are forced upon a ring, just to show that we can't always expect dualizing complexes to exist. So one can show that if I take a minimal injective resolution of my omega r, then I actually know what the modules here look like. I'm not going to describe the differentials, but the modules are not too bad to describe. So at the end stage, this will look like so I'm taking a direct sum over all P in spec R, and I'm looking at the injective hull. So just as a brief recap, what this is supposed to be is this is an injective module over R, injective over R, which contains R mod P, and it's the smallest such injective module. This is called the injective hull. And so at the end stage, I'll actually be looking at those primes for which this, one can call it the co-height, this is equal to n. So this, what I began with was a minimal injective resolution. And I'm lying a bit because if I shift something, things still remain the same. So I'm saying up to shift. So I'll normalize this to make it as following. And maybe also let's assume that it's RMK local here. So in the zeroth, so the normalization is made precisely so that the zeroth spot is just going to contain one injective module, namely the injective hull of the residue field. It is fairly simple to see that if omega r is dualizing, then any shift of omega r is also dualizing. So I do need to make some normalizing hypothesis. And for a local ring, omega r is unique up to these quasi-isomorphisms. And so in fact, this is a description of it. But of course, I've only described the modules that are appearing, not the differentials. And why am I saying that this is actually going to put some restrictions? Because this actually fixes the location of each prime. It's in some sense, it's telling you that if you look at the coset of all primes, there is a very specific place where it should appear. And amongst other things, what this implies is that R is catenary. Which is to say, if I have two primes, one contained in the other, then every maximal chain of primes between them have the same length. But not all, not even local Noetherian rings have this property. So for example, there's the example of Nagata, where he constructs a ring such that you have primes, you have maximal chains of prime which look as follow. So it's in fact, what he constructs is a three-dimensional local domain, which is Noetherian. And this exactly is a 3 and 2. Also, from this description, we can look at its connection to matless duality. If you don't know what that is, I'll give a recap. So let's say that this functor I denote with a dagger. Suppose RMK is local. And assume, let's say that omega r exists and is normalized with this convention. Suppose M is an R module of finite length. What this, in particular, this implies is that M is M power torsion. That is, M to the n is 0 for large n. In fact, one can pick the length and do it by the definition of finite length. You have a filtration, and the only simple module is this. But what does this mean? If one is somewhat familiar with the description of these injective hulls, one of the things that one sees is that these injective hulls are actually modules over the P localization. So if I take a properly contained prime, if I take a prime P which is properly contained in M, this is killed by a power of M. But if I pick something which is in my maximal ideal but outside of P, it will act as a unit on this, but it will still kill this. So this harm will become 0. So all of these harms will become 0 if P is properly contained, which is to say that if I just do R harm of this, the derived harms can be computed using an injective resolution. So I'll just be left with the usual harm of M, comma this, but this will only survive in 1 degree. So I will just get the injective hull of the residue field. And matless duality precisely talks about this functor where I take harm into the injective hull of the residue field. So local duality is a generalized version of matless duality. So this is more or less the general duality picture that I want to discuss regarding Gorenstein rings, and then I'll define what they actually are. Any questions so far? That it exists. That was more or less. I didn't give any hypothesis. So one can show that if it exists for R, then if I take any finite algebra over R, it will still exist. You can actually just localize and get it. And you can also, finitely generated, not localize. You can do it over polynomial rings and quotients. And then localizations of it, you can still get dualizing complex. So a large class that you can think of will have these things because K is a Cohen-Macaulay thing. So for any K, you have the canonical module. You don't need it itself is it. So you can do it for all K algebras and all localizations of K algebras. Yeah. But you have some sort of restrictions, just catenary. And I didn't talk about uniqueness much, but these are also essentially more or less unique. For local rings, they are unique, only the shifts is what you can do. But for non-local rings, you can also tensor with rank 1 projectives. And what that means is that you have a module such that you have a projective module such that localization at every prime is a rank 1 free module over the localization. And that's more or less all you can do. And given the question of when do they exist, one case in which they will exist is if my R is Gorenstein. And by definition, I'll tell you what it means. So let's say if I have a local ring, R M is subset is Gorenstein. If injective dimension of R is finite. And it is easy to see that 1 and 3 are always true for any R. If I just take omega R equal to R, it's always going to satisfy the first and third condition. It's precisely that second condition which I have defined in my definition over here. So Rm is Gorenstein if the injective dimension is finite, and as is sort of usual in commutative algebra, once you have a definition for local ring, a general ring R is Gorenstein if Rm is Gorenstein for all maximal ideals. So you might be wondering why I didn't just define it directly in this form. And the question is, I could have defined Gorenstein to just mean that the injective dimension is finite. And that is not always equivalent. If the cruel dimension of R is finite, under this hypothesis, R being Gorenstein is equivalent to injective dimension being finite. But what I'm talking about will include some infinite dimensional rings also. So for the hardcore commutative algebraists, you might have seen an exercise about there do exist Noetherian rings which have infinite cruel dimension. And again, it goes back to an example of Nagata. And the usual exercise which one sees, that ring is actually all the localizations are in fact regular. So they are in particular Gorenstein. And since I'm talking about regularity, let me just remind. So R is said to be regular if the so-called global dimension of R is finite at every localization at a prime. And just to recall what global dimension means, one way of defining global dimension is take the supremum over all possible injective dimensions and or all possible projectives, but injectives will directly give us that regular rings are Gorenstein. So the example of Nagata, which is an infinite dimensional regular Noetherian domain even. So that will fall under the category of infinite dimensional Gorenstein ring, which has not only infinite cruel dimension, but also infinite injective dimension. So then one might ask, why do I want to morally consider those rings as Gorenstein? And for that, there's the following fact that Gorenstein, in our sense, is equivalent to this functor, which is the functor I was considering, this functor inducing an autoequivalence on dB. And I suppose we all agree that duality is important because we are in this workshop. So this is why I still want to consider infinite dimensional rings to be Gorenstein, even though in practice, none of the rings which I'll talk about today are going to be infinite dimensional. So regular rings are also not that ubiquitous. So let's also see one more result. So let RMK be local. When I say local, I also mean Noetherian. And let's say that X is a non-zero divisor. Then one has that R is Gorenstein if and only if R mod XR is Gorenstein. Why is this good? Because the words regular sequences have definitely been mentioned. And this shows that if I want to check something is Gorenstein, I can go mod a regular sequence and check it. Conversely, if something I have is already written as a quotient of something mod a regular sequence, I just need to check the thing above. And since regular rings are Gorenstein, this gives us one more implication here, that complete intersections also imply Gorenstein. So we have this chain of implications, and one implication that one always has is that Gorenstein implies Cohen-Macaulay because, well, the canonical module exists, for example. So we have this chain of homological implications. And none of these implications are reversible. So we will see some examples today. And I will just give one more characterization of Gorenstein rings before moving on to the promised examples. So let's say RMK is local Noetherian as usual. Then the following are equivalent. So one, that R is Gorenstein. And two, if I compute this X of K comma R, this should be 0 when the index is not the dimension, and it should be K when it is the dimension. In fact, this can be refined further. For example, if X vanishes for large enough n, or if X is 0 for every n smaller than the dimension, etc. But this was also something which Professor Greenlees had mentioned in his talks, and I am to believe that this is actually how one can then define what a Gorenstein space is, because there is some topological thing to be put here, and you can take this as your definition of a Gorenstein space. And now let's move on to the promised examples. Let's see. So injective dimension being 0 is one special case of injective dimension being finite. And we've seen examples of this in the form of group rings. So K is any field, and G is a finite group. Then KG is a Gorenstein ring. So I haven't defined what Gorenstein means for a non-commutative ring. In the non-commutative ring, I will take this to be my definition, which is what Professor Henning had described as a Iwanaga Gorenstein algebra. Just that the injective dimension is finite as the right module as well as the left module, in which case the injective dimensions coincide. But this is a Gorenstein ring in a very special way. It is self-injective even. So this may not be very surprising in the commutative case that it's self-injective, because this is an Artinian ring and one can show that the dimension will become the injective dimension. But in the non-commutative case, it's interesting, I suppose. So we will see some more explicit ways of seeing this. So, okay, let's look. So this was, in fact, Nabha had mentioned in his talk that if we have Z cross N1, Z cross N2, and so on, a product of cyclic groups, this is actually just KX1 to XR and modulo X1 to the N1 minus 1. This is my group ring, and all finite groups are of this form. And this is going to be Gorenstein because it is a complete intersection. And before moving on, I had said this implication cannot be reversed. But there's actually one extra condition that I can add on to that, which will make the implication of Gorenstein to Cohen-Macaulay reversible. So again, let's say RMK is local. And let's say D is the depth of R. So the depth of R is the length of the longest maximal, the maximal regular sequence contained in the maximal ideal. They all have the same length. So that's called the depth. And then one can define the type of R to be the rank as a K vector space of this dth x of K comma R. Yes. And this may seem like a bit contrived or out of nowhere, but it's not that bad, this definition. So if you recall, I had this sort of description over here, and these modules are actually the building blocks of all injectives. And one actually has a very precise count of what injective resolutions look like. So what is the count of modules appearing in an injective resolution? So if I take the injective resolution of R as an R module, and if I look at the dth spot, I'm just counting the number of copies of ER, R mod M that appear in that dth spot. And that is called the type of R. We have this, and theorem is R is Gorenstein, I'm in the local setting, if and only if R is Cohen-Macaulay and the type of R is 1. So Gorenstein always implies Cohen-Macaulay, and type R being 1 is enough to do the converse. In fact, with this definition of type, Roberts proved that just type 1 is enough. So we have these implications. And these are particularly nice if we are in the 0-dimensional case. Because if we are in the 0-dimensional case, rings automatically become Cohen-Macaulay. So this is again a result that the depth is always bounded above by the dimension, and it's non-negative. So if the dimension is 0, then the depth is 0, and my ring is Cohen-Macaulay. So let's say that dimension of R is 0. So R is Cohen-Macaulay, in which case, so this theorem is not a deep theorem, so we can use this without feeling bad that we don't know a proof. So this Cohen-Macaulay is already taken care of. Then I have the following equivalent conditions. 1, R is Gorenstein. 2, type of R is equal to 1. But let's see what is type in our case now. So D is 0. So what is the 0th ext? Hom. So the 0th ext is just Hom. So I'm saying that rank of this as a K module is 1. But that is just saying this. And in our specific case, this also can be interpreted in a different way. So K is a cyclic R module. It is R mod M. So this Hom can be interpreted as, to define a map from K to R, I need to give you an element of R, which is killed by M. And that's precisely the data. So what I'm doing is I'm looking at M, and I'm seeing what are the elements in R which take it to 0. So that's my notation for this, which you may know as the annihilator of M. And this is also the largest submodule of R, which is also a K module. So I can still talk about its dimension over K. And this is 1-dimensional, is the equivalent condition. And this is what is called the socket. And this is sort of the beauty of the 0-dimensional case, that these things are very explicit to compute for, at least if I'm looking at the K algebra and going mod some homogeneous, if I'm looking at a polynomial ring mod homogeneous elements. And I will indeed consider those examples. Yeah. It is the depth, yes. Yes, according to Shri, yes. Okay, yeah. And yeah, so hopefully the fact that these three are equivalent is clear just by definition of X and how I defined this is more or less just this. And it's also equivalent to being Gorenstein by this result. And let's apply this explicitly now to some examples that we have seen. So let's look at this example, AXY mod x square comma y square. And this already came up yesterday in Professor Henning's talk. This was the, if K was F2 at least, this was the group algebra of the Klein-Four group. And this should be Gorenstein. but we'll see explicitly why. So I'll draw the same picture that he had drawn. So kxy mod x square comma y square, it is a finite dimensional k vector space. You see this, you can think about the monomials, and you'll see we've actually killed pretty much all the monomials except one, x, y, and xy. These are the only monomials which are there. And this is the picture that he had drawn. We multiply with x. When I'm multiplying with x, I'll make an arrow to the left. And then he multiplied with y. We get this, and the other way around here. Also, my convention will usually be that in the quotient, I will denote my variables with little letters. So these will be the images of the capital letters. And yeah, so every other monomial is actually zero. You can convince yourself by some sort of a pigeonhole argument. And the socle is actually just this guy over here. How do we see that? Well, if I multiply this with x or y, it is indeed zero. So that is definitely in the socle. And now the socle is a vector space, so you can sort of just look at some sort of a basis and conclude things. So at least for these three, it's clear that these are not in the socle, because this, if I multiply with y, I'm ending in something non-zero. This, if I multiply with x, it's something non-zero. And for one, it's clear as well. So this is Gorenstein. Which is good because at least in the k equal to f2 case, we had a group algebra. Now, similarly, let's see something which is not Gorenstein. By the way, this being Gorenstein could have also been seen because I've gone mod a regular sequence. Now let's take something which is not Gorenstein. There was one thing extra over here. What if I kill that as well? Now my picture is not going to be so closed. By that, what I mean is, this is how my picture now looks. And now I have two things inside my socle. So this is not Gorenstein. And this already proves that this implication can't be reversed, because both of these rings are Cohen-Macaulay. In dimension 0, everything is Cohen-Macaulay. I'll give you one example of a higher dimensional Gorenstein ring, a class of examples rather, and then we'll come back to this more fun and checkable by hand case. It's a theorem of Watanabe. So let K be a field of characteristic 0. And let's take a finite subgroup of GL and K. So GL and K has a natural action. So this acts on the polynomial ring. Because it acts by graded K linear automorphisms. Because so x1 to xn is a basis. So you can think of x1 to xn, you put it in a matrix, multiply it with the element of GL and K, you'll get something at the other end, and then you extend it by ring operations to the full polynomial ring. So let's call this S. So then I can talk about the fixed subring. So in Galois theory, one would have seen that if you have a group acting on a field, one talks about the fixed subfields. Similar to that, I can talk about the fixed subring, and I can talk about it being Gorenstein. So when is this Gorenstein? One condition which implies this is that G is a subgroup of SLN. Let's look at some examples of this. So let's take K equal to our nicely behaved C, and G, let's take it to be a cyclic subgroup. It has to be finite. So let's just look at this subgroup generated by the scalar matrix where zeta is a root of unity. So I'm putting the same zeta, so this is a group of order n. And in this case, SG is going to be, okay, for ease of exposition, I'm just taking n equal to 2. So in this case, XG is going to be the dth Veronese. So this is the subalgebra generated by the degree D monomials. It's easy to see that these are all fixed, and it's not too difficult to argue that these are exactly what's fixed, because this is actually not just graded, it's like multi-graded. So you can just look at what monomials are fixed, and these are the only ones that will pop up. But when is this a subgroup of SL2? It's not very often. It's only if zeta is either 1 or -1, because so SG is Gorenstein if D is either 1 or 2. Or more generally, if I had put an n over there, it would have been if and only if D divides n. And there are these awkward one implication arrows, so I'll just complete the picture. You also do have the other implication, provided G contains no pseudo reflections. And what is a pseudo reflection? So an element is, so a matrix G is a pseudo reflection if this is true. If when I subtract the identity, the rank is 1, which in diagonalizable cases is saying that all the eigenvalues except for one of them is exactly equal to 1, and one of them is not. These don't contain any pseudo reflections. So so this is Gorenstein, but any higher one will not be. And more generally, if I had n variables and I was looking at the dth root of unity, it would be Gorenstein if and only if D divides n. These are all again Cohen-Macaulay. So this gives you a domain example of something which is Cohen-Macaulay but not Gorenstein. To see that they are Cohen-Macaulay, one can note that this subring will split as a direct summand of the polynomial ring, and Cohen-Macaulay behaves well with that. These are integral extensions. Yeah. So we have this. Yeah. Now I'll move on to the large class of examples which somewhat more motivates that Gorenstein is a condition about symmetry or duality. So this was, I'll erase this example. And the nice thing about this is if you had been lost at some point earlier, you can jump back in, because all of these examples are very easy to test. Like more or less by hand, you can test these things. So let's go back to a theme like this. So here we were not in the local case, but we were in the next best sort of nice case, which was graded. And let's look at what are called Poincaré algebras. So what are these? So R is now going to be a graded ring with the zeroth part of field. So I'll write it as follows. Just so that I'm not doing anything silly, the last part is non-zero. And let's say R is either it's commutative on the nose or it's graded commutative. Now I want to characterize when is this Gorenstein, and my everything is Noetherian, so the dimension of R as a K vector space is finite. So this is a graded commutative K algebra. It has the usual grading. So we have these pairings. So just being graded means that if I multiply something in component A, component B, I get something in component A plus B. Or a special case of that is if I take I and D minus I get something in D. And the usual sort of adjunction tells you that a bilinear map as following is the same data as a linear map from Ri to Hom Rd minus I, comma Rd. So these two are the same data. So this is bilinear and this is linear. And now I'll write down some equivalent statements. R is Gorenstein. So again, in the non-commutative case, I mean that finite injective dimension. And these are anyway finite dimensional things. This is equivalent to this pairing being non-degenerate. For all I, and that Rd, the top piece, is actually one-dimensional. And so again, this is the main thing. This is seen equivalent to rho I as an isomorphism for all I. This is not too difficult to see. And yes, this multiplication is the one induced by the graded structure here. Yes, R is a zero-dimensional. If in the dimension, at least in the commutative setting, yes. It is finite dimensional over K, so it has dimension 0. And again, since it is dimension 0, I can rewrite this as Hom R comma K as the Hom is computed over K, but this should be isomorphic to R as graded R modules. And since I'm saying graded, I'll actually mention what that shift is supposed to be there. So once I shift, it should be isomorphic to R. And I've suggestively called this a Poincaré algebra. And again, as was mentioned today as well, Poincaré duality gives a large class of such algebras. So let's say M is an n-dimensional compact manifold. Then, as one proves in an algebraic topology course, that the cup product on the cohomology ring, it is a perfect pairing. It is a non-degenerate pairing. It's called a perfect pairing, or even Poincaré pairing, maybe. Yeah, so in this case, if I look at the cohomology ring with the cup product over F2, so it's actually commutative because there are no signs. So this is Gorenstein. This is like Poincaré duality implies this at the very least. And if suppose my manifold were even orientable, then I could have replaced F2 with any old field. So this is one example. And we can construct many more examples just by hand now. So what do I mean by that? So to construct such an example, I need a pairing like this. And one easy case of just having to define one pairing is the following. I'll take, so let V be a vector space over K, finite dimensional. And let's say that I have given it a bilinear form. Then given this information is enough to describe a graded ring structure on R. And just so that we're not doing something too bad, I'll assume that this form is either symmetric or anti-symmetric. Symmetric will give me a genuine commutative ring. Anti-symmetric would give me a graded commutative ring because this one is in degree 1. So we have this. And so now R is Gorenstein precisely if this is non-degenerate. Oh, yes, thank you. Yes, yes. Both of these can be checked using this now. Because, okay, technically this one requires the more general one, but this one can be checked using this exactly. And in fact, this tells you that what does it mean for something to be non-degenerate? Well, every bilinear form can actually be written as a matrix. You multiply on the left and on the right by column and rows. So this is, in some sense, this gives you a bijection with symmetric invertible matrices or anti-symmetric invertible matrices. So both of these can now be checked using this. So this one cannot be Gorenstein because the top piece is not one-dimensional. And this one is Gorenstein because the top piece is one-dimensional and this is a non-degenerate pairing. If you were to write down the matrix for the pairing, that would turn out to be invertible. And one consequence of this is also the following, that I'll just write it over here. If we are in this, if one of these things hold, then the rank of the ith piece is the rank of the d minus ith piece. So this again is some sort of symmetry. It's a palindrome if you read it out. But now I'll give an example to show that just being palindromic is not good enough. So let's look at that. So let's say R is kxy mod So here, when I went modulo these three elements, I lost everything on the top. So the top was not one-dimensional. So let's say I want to keep x square in. So I won't kill it right off the bat, but I'll make x cube 0. So what things survive now? Well, I have 1, I have x, I have y, and I have x square still remaining. And these are the graded dimensions. So this dimension 0, it's 1, then it's 2, then it's 1. So the Hilbert series will actually be a palindrome. But I claim that this is not Gorenstein. And if we actually draw the picture out, it is somewhat clear that even though if I just drew the vertices are the same as the vertices over there, but drawing in these edges makes things more illuminating. This is now a Socle element, as would be expected. There's nothing above it. So this would definitely have to be, anything in the top layer would have to be Socle, because multiplying would send it above. But even y is a Socle element now. And that is the issue, that the Socle is not one-dimensional again. And if we were to use this perspective, in this case, again, we do have some sort of a pairing. So x square is non-zero, but yx and y square are both 0, which means that the non-degeneracy is not satisfied. It is degenerate. No matter what I multiply with y, I'll end up in 0. So this is not Gorenstein. But if I were to compute its Hilbert polynomial, it would be palindromic, which is what this had said, that Gorenstein would imply palindromic, but the converse is not true. We have this. Let's look at a somewhat bigger example. So I said that I can describe my pairing using matrices, square matrices. So let's look at a three-dimensional case as before, and my pairing is given by this. So if I were to again suggestively write this basis as, let's say, V as kx, ky, kz, then what I'm saying is that xy, yx, and z multiplied with itself, these give me the basis element here, let's say capital T. And everything else is 0. By that, what I mean is if I multiply any other combination of x's, y, and z's, I get 0. This is invertible. So what I end up with is Gorenstein. It's easy enough to see using this criteria that it is Gorenstein. And why am I bringing this up? Because for this, it's not very difficult to describe what that ring actually is. So let's see, what am I doing? I am killing x square and y square. I am making z square equal to xy. So that's another relation which I have. I won't write xy equal to yx because we're in the commutative setting anyway. Are these all? No, because I want to take more of these relations. So what am I missing? I'm missing xz and yz. So xz and yz are the zeros over here. And this is a minimal generating set, what I've written at the bottom. And why am I saying this? Because I have a 0-dimensional ring and it's 3 variables mod 5 generators. And you can check you can't do better. So this is not a complete intersection. So I have promised examples of the reverse inequality, reverse implications not holding. We have this. I'll also mention some more examples in higher dimension, or rather I'll mention some facts in higher dimension, which again make these computations not too bad. So when we're working with group rings, especially these things, it's fun to compute these things and check what we have. So let's say R is a non-negatively graded ring, Noetherian, finitely generated, or it's Noetherian. R naught is a field. I think that's all the good assumptions I want. And so there's this notion of a Noether normalization. So let A inside R be a Noether normalization. And just to recall what this means, so every finitely generated K algebra, inside it, you can actually find a polynomial ring. And the good thing after finding that polynomial ring is that this R is a finite module over A. So to begin with, R was a finitely generated K algebra, but being finite module is an even stronger condition. And this says that you can actually find something nice between K and R. So A is polynomial over K, and R over A is finite module. And why is this nice? Because in this graded world, we can check our known definitions using other criteria. So first, R is Cohen-Macaulay. If R is a finite free module over A. That's nice. We explicitly have a basis. On top of that, R is Gorenstein. If R is Cohen-Macaulay and Hom over A of R into A is isomorphic to R up to some shift. As graded R modules. This shift is not known, so I'm just going to put there exists some Z. Now the similarity to this one. In this case, since we were in the zero-dimensional setting, zero Krull dimension, K itself was a Noether normalization. So in general, we replace K with the normalization, and there we were in a good enough setting that we could actually comment about what that shift should be. In general, we have this result that up to some shift. I know that this isomorphism is as R modules. Once R is Cohen-Macaulay, this isomorphism as A modules is sort of clear because it's the usual thing with free modules. You can count the ranks and get the result. But isomorphism as R modules, in particular, that left Hom should be cyclic as an R module. And oh, I've erased some pictures, but yeah. For example, so let me erase this. The cyclicity as an R module, more than cyclic, it should be free, but just the cyclicity can also be interpreted using these diagrams. So taking the Hom is just going to flip this picture. So you can think of this as a mirror and you get the dual basis. So here my Noether normalization is K, and I already had a K basis. And the dual basis, one knows what it does to the things. And now one can actually check, does this form an R, do you have a graded isomorphism? And sadly, we do not, because it's not cyclic. You can't go from, if it were cyclic, this would be the generator because it's in the lowest degree. You can only increase the degrees, but you can't go from here to here. That's, yeah. And this perspective I got from my discussions yesterday with Professor Anita about how this is quite literally the dual. We have this, And this also, I want to erase that. Let me erase this one. So in the setting that we mentioned over there, with A being a Noether normalization, one can actually compute the Hilbert polynomials, the Hilbert series, quite nicely. And by that, what I mean is, so the Hilbert series of a polynomial ring, if I just had A over here, it's sort of easy to compute that this is going to be 1 minus t to the number of variables, or if I'm not giving it the standard grading, I can just write it as a product of 1 minus t to the whatever degrees I have given to it. So this 1 over this would just be the Hilbert polynomial, Hilbert series of the polynomial ring. But now suppose if I have a Gorenstein ring, the fact that it's free over the Noether normalization, just being Cohen-Macaulay, actually tells me that this Hilbert series will not be very bad. It will just be this. So what are these CJs? I pick a basis for R over A, and then I count how many generators do I have in degree 0. That's C0, C1, C2, and so on. So R being Cohen-Macaulay will give me this. But R being Gorenstein now does something better. Why? Because if I have a basis for R over A, for the dual, I get the same basis, but now the elements all have negative degrees. So R Gorenstein will tell me that this sequence is palindromic. So I've skipped a few steps, but essentially the point is that if I want this to happen, I will negate all the degrees here. So it'll become Cj t to the negative j. And then because of the shift, I have the liberty to multiply with some t to the q and t to the q, and then I will multiply it just enough so that I can compare the coefficients and I'll get this. And so the way I have written this, in some sense, it depends on how I've picked my denominator and my numerator. So a more inherent description is the following. That if I take the inverse, I get the same thing again. Not so easy. I have some shift. And once I'm pulling things out, I'm picking up a sign. And I'll pick up exactly the dimension of R. So R being Gorenstein implies this. And this is the first thing that Professor Greenlees had started out with in his first lecture. This is, again, a statement of symmetry. And this does not characterize Gorenstein rings, because we already saw this was not Gorenstein, but it had a symmetric Hilbert polynomial. But there is a theorem of Stanley suppose R is a Cohen-Macaulay graded domain. Then R is Gorenstein if and only if this holds for some q. And that's actually how one proves, or at least the proof which I have seen, of Watanabe's result. Because for over characteristic 0, one actually knows what the Hilbert series of the invariant subring is. It's calculated just using the characteristic polynomials of your elements in the group G. So we have this, and we have 10 seconds and 5 minutes. There's one last result which I'll mention, which is again something Professor Greenlees has done in his first talks and even in the ones afterwards. It's the following. Suppose we have a monoid. So monoid means that it contains 0 and it's closed under finite sums, such that its complement is finite. If I have this, it's called a numerical monoid. I can consider, actually, this is something which we've seen, the group algebra, but I don't have a group, I have a monoid. I can consider the monoid algebra. And in case you haven't seen this before, this is just a abstract way of writing kx, because that's essentially what it turns out to be. In fact, Nabastock had said how if I had z here, then I would have kx comma x inverse. So this is believable. And this will turn out to be the subring generated by monomials corresponding to those in sigma. And under this result, under this setup, K sigma is Gorenstein if and only if exactly half of the elements in 0, c minus 1 are in sigma, and I haven't defined what C is. So if you notice that this is finite, which means that after a point, everything is going to be in sigma. So C is the least element in sigma, such that everything from that point is contained in sigma. So exactly half of the elements should be in sigma. That's the equivalent condition to Gorenstein. And this is again palindromic, because this being half actually turns out to saying that the wholes are anti-palindromic. So I'll just give a quick example as to what I mean by that. So if I look at the example, which was the one being considered quite often, x to the 5 and x to the 8. So x to the, yes, thank you. So x to the 6 is here, x to the 7 is not. X to the 8 is here because of 5. X to the 9 is also here, and x to the 10 is also here. Once these three are here, everything afterwards is also there. So my C is 8. So now if I look at 0, 1, 2, 3, 4, 5, 6, 7, 0 is there by definition. 7 is not there. 1 is not there, but 6 is there. 5 is there, and 2 is not there. 3 is there, 4 is not there. So these wholes are anti-palindromic. And he mentioned that if we throw in x to the 7, then things go wrong. And indeed they do. X to the 7 is now erased. So my largest C will actually be 5 now. And I am left with this. And now it's not palindromic anymore, just by parity arguments. And yeah, that is all that I had to say about this.
Questions, comments?